This is lesson 1.3, graphs and their derivatives. Today's learning goal is to be able to graph the derivative of a polynomial function, and you'll be familiar with graphing functions using their end behaviors and some key points in those functions from your grade 12 function class. So we're going to review the characteristics of a function that we need so that we can graph a function, and then we're going to go ahead and use our knowledge of graphing and slope of the tangent at key points on the function to graph the derivative of the function. So let's take a look. Let's just do a little bit of review. And I've gone ahead and I've written down a few things about what we need or what you would have learned in grade 12 in order to be able to graph a function. Well, you need to know the end behavior. So you need to know if the degree is even and the a value is positive, that we are going to end up with a positive situation or an up situation. You also need to know what happens if it's an even degree but a negative a value and it's down. If it's an odd degree, meaning that the power that it's raised to, like in our example here, 2x cubed, is raised to an odd degree, but our a value is positive, then it's going to go up to the right and down to the left. And if it's an odd degree and a negative a value, it is reversed. The other thing that we need to be able to know is what are the x-intercepts and what are the y-intercepts. That just gives us a couple of points to be able to graph. We need to know about the symmetry, what translations are happening or what's happening as it crosses the y-axis and the origin. We need to know the maximum number of turning points, and again we're going to use the number of degrees to be able to figure that out. We want a few more points. We're just going to plug some values around the point we're looking at into the equation, and then finally that should give us enough information to sketch. So let's start off by taking a look just at the end behaviors. So our equation that we're going to look at is y equals 2x cubed minus 3x squared. So the very first thing that I want to do is I want to take a look at what's happening here. My a value is positive and my degree is odd. So that tells me right off the bat that I know this graph is going to rise up to the right and fall down to the left. And we're going to make a little bit of an assumption on our graph that it's going to look something like that. Just given the fact that we know a cubed function, we know what a cubed function is supposed to look like. We just have to figure out what that 3x squared is going to do in the middle of it. The next thing that we want to figure out are the x-intercepts. And we're going to do the x-intercepts the same way we always have, by pulling out a greatest common factor and then figuring out the turning points or if it passes through. So let's look at x-intercepts. So I have my function of 2x cubed minus 3x squared. I'm going to pull out a greatest common factor of x squared. That leaves me with 2x minus 3. And then I'm going to go ahead and I'm just going to figure out each one of these separately. So my x squared is an even degree. So an even degree, if you remember, tells us that it's going to be a turning point. And that turning point is when x squared equals 0. X will equal 0, so it's going to turn at 0. So we know at 0 that it's going to turn. So we can put that point on the graph. So we know at the origin we're going to have something turning around. Now the other one is telling me, so this 2x minus 3 has an odd degree. So it's an odd degree, which means that it passes through at whatever point this is going to be. So 2x minus 3 equals 0. So x equals 1.5. So when x equals 1.5, we can put that point on the graph right here. We know that there's going to be a little bit, it's going to pass through. So we know whatever else is happening, it's passing through here. But now we need to know what's happening down here. And we need to know a few other things. Okay. So the next thing that we want to know are our y-intercepts. So that was our x-intercepts. Now let's take a look at our y-intercepts. And remember, our y-intercept is just where x equals 0. So we're going to use our equation and just plug in the value of 0. So f at 0 is equal to 2 times 0 cubed minus 3 times 0 squared. And I think you probably already came to the same conclusion that that equals 0. So that gives me a y-intercept of 0, 0. So I've already got that on there. So we know that it's turning here. So we know that it's turning here. So now really what we're left with is figuring out what's happening down here, and this is where the symmetry is going to help us with that. So where do we want to put that? I'm just going to sneak down here, and now we're going to look at symmetry. Oh, what is happening? Now we're going to look at the symmetry. So when I have a function 2x cubed minus 3x squared, and I want to figure out what it's doing around the y-axis, really what I want to know, does my negative x value equal my parent function? So if I plug in a negative x value in there, will my parent function be the same? And in this case it does not, meaning it's not symmetrical around the y-axis. So if I were to plug in a negative x value into my equation, I get 2 times negative x cubed minus 3 times negative x squared, which gives me negative 2x cubed minus 3x squared. So my negative x value does not equal my parent function, therefore not symmetrical around y-axis. Now let's do the same thing around the origin. So that's around the y-axis. Let's look at what's happening around the origin. So around the origin, remember, both things, both your x's and your y's are changing values to be negative. So what we're looking for here is that our negative x values equal our negative y values. So negative f of x equals negative of the whole thing, 2x cubed minus 3x squared, which equals negative 2x cubed plus 3x squared, and they do not equal each other. Therefore, they are also not symmetrical around the origin. And we kind of already knew that just looking at our graph, because we know that something is happening over here that's making it not symmetrical around the origin. Okay, so now what we want to do is we want to figure out how many turning points is this going to have. So let's go, I'm going to change color pen just to try and keep everything straight, and I'm going to go back and number these after. So now we want to know the number of turning points. So where does this turn around? So if my degree is 3, at most, remember, we'll have 3 minus 1 turning points, so we'll have 2 turning points. That's my maximum that I'm going to have. We know that there's one at 0, 0. Now we just need to find more points to figure out where the other one is going to be, and that takes us to our next part of finding more points. So to find more points, we're just going to take some x values that are hovering between, or not hovering between, but that are between 0 and 1.5. And why 1.5? Well, because that's where I know I've got something going on here. Okay, so this is what I need to figure out. Is this a turning point, or is this going to be, well, we need to figure out what's going on there. Okay, so I'm going to take an x value of 0.5. I'm going to use 1, and I'm going to use 1.25. That's getting closer and closer to 1.5 from the 0 side. And when I fill in for my function, I get y values of 0.5, negative 1, and negative 0.78. This is telling me that this turns here. So it's turning when x equals 1 and y equals negative 1. So it's turning right here. So now all that's left for us to do is sketch this, because now we can fill in the blanks. And I'm just going to erase this end behavior just so I can make this look a little bit nicer. I don't know why that's doing that. Okay. Doesn't want to erase, so we're just going to leave it. Okay, so now I know that I'm turning. I've got my, oh, it did erase it. I've got my turning point right there. And so there you go. We have sketched this graph. We're going to lean into this for what we're about to do next. So I've gone ahead and sketched this graph on Desmos just to make sure that we did sketch it correctly by hand. That's not a bad thing to do if you aren't sure that you've sketched it correctly, is to lean into Desmos and its graphing capability. So this particular graph in this example is actually on the handout that I posted. So if you don't have that out, you should probably go and grab that now. So when we're talking about instantaneous rate of change, we want to look for some key points. So we just want to know the trends really at those key points. So we want to know, when is the instantaneous rate of change equal to 0? So where is the slope of the tangent 0? Well, we have 2 points on our graph where that tangent is 0. We have right here, and we have right here. So anywhere that, so the tangent point and the slope right there at those turnaround points is going to be 0. So if we want to fill that in, we can say that the instantaneous rate of change is equal to 0 when x equals 0 and when x equals 1. Now we want to know, when is the instantaneous rate of change greater than 0, or when does it have a positive slope? When does that tangent line, if I put a tangent line on any point in this section, will it have a positive slope? And what we're looking for is where it goes upwards. So we can see that from 1 upwards to infinity, because remember this is going to keep going forever and ever and ever, to positive infinity, we have a positive slope there. So we can say that we have an interval from 1 to infinity, but we also have another interval where it is going up and to the right, and that is this interval right here. So while this line goes all the way down to negative infinity, this section of the graph is actually coming upward, and so we would say that is a positive slope. So we can say we have another section of tangent that would be positive from negative infinity to 0. Not surprisingly, the next part that we want to look at is when the instantaneous rate of change is less than 0 or has a negative slope, and there actually is only one spot on our graph where that happens, and that is between 0 and 1. We have a negative slope right through there. So we are going to say that that is between 0 and 1. Between 0 and 1. So we would write that x will be less than 1 and less than 0. So when x is less than 1, it has a negative slope. When x is greater than 0, it has a negative slope. So now the last piece that we need to figure out on here is, when is the instantaneous rate of change at a minimum? And I guess what I need to do at this point is fill you in on what I mean by a minimum. And we're going to look at another example first and then come back to this one, just so that we can see what's happening. Okay, so how do we figure out the maximum and minimum instantaneous rate of change? Really what we're asking is, at which point on this particular graph will the IROC be a maximum and a minimum? Well, let's take a look at the maximum rate of change first. And really what we want to do is we want to take a look at the slope of different tangent points all along this curve at strategic points though. So let's add some points on here. So I'm going to make this bigger. And let's call this point A. We'll put a point halfway up here. Let's call this point B. We'll make the very tippy top C. We'll make this point D. And then right down here, we'll make this point E. Now, a few things that you might notice as we move along this graph in this direction, we are going from a minimum value at the very bottom at A, minimum value, up to our maximum value at C. And that's going to be important when we start talking about the maximum rate of change and the minimum rate of change. Okay, so I've added some points. Now let's look at the slope. So when we're at point A, my slope is 0. So let's record that. So my slopes at point A, my slope is 0. As I move up this graph, or up this graph, yeah, as I move up this curve, the slopes get progressively and progressively steeper in the positive direction until I get to point B. And when I get to point B, they are very positive. So we can say that from A to B, so from A to B, the slope is increasing. Now let's take a look and see what's happening when we go from B to C as we continue up here. So from B to C, the slope is still positive, but it's getting less steep. So the slope is decreasing. And by the time we get, so if we take a look here, like the slope is less steep. And by the time we get to point C, the slope is back to being 0. So between B and C, the slope is decreasing. And this point right in the middle, where it's positive, 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 is our maximum rate of change, is at B. So the takeaway here is that the maximum instantaneous rate of change occurs midway between the min and max value. Max IROC occurs midway between min and max value. Okay, so now if you had to guess, I would bet that you'd be able to tell me already that the minimum instantaneous rate of change is going to be halfway between the maximum and minimum value. But I want to go ahead and just continue the same process, looking at what's happening for the minimum rate of change. So when we want the minimum rate of change, so the minimum, we're going to look at the slope of the tangent again. So look at the slope. Only this time we're looking at the negative slopes. Okay, so if we take a look back up at our graph, we're going to go from C to D. I'm just trying to get that the right size so we can all see on here. Okay, so at point C, we already know that the slope is 0. As we move along here to point D, the slope is getting more negative. It's decreasing. So by the time we get to D, we have a very negative slope. So as we move, it's becoming more negative, which means it's decreasing. As we move from D to E, though, it starts to not be as steep until we get back to E, where it's back to 0 again, where our slope is back to 0. So this is our less negative. This is less negative, meaning that the slope is starting to increase again. So if we take a look from here to here, it's less negative, which must mean that our most negative point is going to be the slope, where the slope is at a minimum, and that's right at point D, in between. It's the midway point. So slope most negative, slope is the minimum. And what that means is that our minimum instantaneous rate of change is going to be found midway between the max and min. The max and min values. Okay, so now that we've taken a look at this example and we've refreshed our brains, or maybe this is new, now let's go back to our other graph and see if we can figure out where the maximum minimum instantaneous rate of change is for that graph. So now back on our original graph, we're pretty sure that we can locate the minimum instantaneous rate of change, because that minimum instantaneous rate of change is going to be halfway, oh, let's change that color, is going to be halfway between the local maximum and the local minimum so it will be at 0.5, 0.5. So the minimum instantaneous rate of change is halfway between the local maximum. So here's my local maximum. Here's my local min. And the minimum instantaneous rate of change is halfway between the local max and the local min, which puts it at 0.5, 0.5. This is directly from your handout. So the slope of the tangent, or that instantaneous rate of change, plays such an important role in calculus that it's given a specific name, and that's the derivative. And that's really the whole point of this calculus course, up until we get to vectors, is determining the derivative of a function. In fact, the derivative of a continuous function is itself a function, where each y coordinate of the derivative is equal to the slope of the original curve at that point. So here's our curve again. We've got the same one, y equals 2x cubed minus 3x squared. The zeros we found by factoring. Sketching the curve would be easy if we knew where the turning points were, and we've looked at that a little bit already, but let's go back and talk about it again. So from the graph, we can see that there's turning points when x equals 0. So right here, there's a turning point, and there's another turning point when x equals 1. So here's our turning points right here. What's the slope of the tangent to the curve at these points? Well, it's 0. So if I were to want to start to graph this on the graph, I'm going to go ahead and I'm going to say, I know I have a point here, and I know I'm going to have a point here where something is happening on my graph of my derivative. A function is said to be increasing when it's moving up from left to right. So if we take a look at the parent function, or the original function, and we assume that this is going down forever to infinity, the slope here is increasing from negative infinity to 0. So we can say that from negative infinity to 0, we have upward. An upward or positive slope, which means that my graph of my derivative is also going to be upward and positive from that point. Then I also want to take a look and see what's happening, where else does it have that increasing from left to right, and it has increasing from left to right along this portion of the graph, all the way up to positive infinity. So from 1 to infinity, this is also upward. And this upward is another positive slope. So we know from this point onward, it is also, the derivative is also up and positive. So how does this relate to the slopes of the tangents? Well, the slopes of that tangent are both positive. Given the information, we've already started to sketch it, but now we need to know, where will the derivative have a turning point? So we know something has to be happening in around here to make that parabolic shape. Now we just need to figure out what that is. Let's see if I can get rid of that. There we go. And so what we need to know is we need to figure out where the turning point's going to be. And that turning point is where the slope changes direction. So where does the slope change direction? Well, it's going to change direction at what we call the inflection point on the original function. And this is where the slope on the original function changes direction from increasing to decreasing, or vice versa. So if we take a look, I'm just going to give you a little bit of a different example. So if this is part of my curve, and I'm looking at where my slope is increasing versus where it's decreasing. On this part, if I draw my tangent, my slope is increasing. And down here, if I'm tangent, my slope is decreasing. And if you remember, we called that point the minimum instantaneous rate of change, and that is actually where the turning point of the derivative is going to be. It is going to relate to that inflection point right here. So we are going to have a turning point on our graph that relates to that inflection point. This part of the handout just really repeats that exact same thing, but I'm going to go ahead and just fill in this information anyway. Oh, where'd we go? There we go. So what points in the original function would become zeros in the derivative? Well, the turning points. So the turning points, that's the zeros of the function, or the derivative, and that is where the slope is equal to 0. What points on the original function would become the turning points in our derivative? Well, we want to know, where does the slope change direction? And it's going to change direction at the inflection point on the original function. And that will be our turning point on the graph of the derivative. Let's look at three more examples other than the one that we've just done. And these are on the handout that I posted for today. So if we were to graph the slope of the tangent at any given point, what would it look like? So let's look at this first one. Let's call this number 1 right here, and let's look at it. So remember, what we're looking for is where the slope is positive or negative. First thing I'm going to do is I'm going to put my point on the graph where I know it's passing through. And remember, that corresponds to where the slope of the function is 0. So that's going to be that point there. So now I need to know what's happening before there and what's happening after there. So this is where I'm going to take a look at what the slope is looking like. So we have a negative slope coming down this way. So we have negative slope coming down that way before we get to that turnaround point, which means that my derivative is going to be down and to the left. Then if I look after my turning point, my slope is becoming positive slope, which means that my derivative will have a positive slope as well. So we end up with a straight line from the derivative of a parabola. Sorry, I drew a complete blank there. And that is going to match to that graph there. Now let's take a look at this one. Let's call this one number 2. Same thing. We're going to start off with the turning points where we know the slope is 0. So where my slope is 0 on here will be here, and it will correspond to here. That means that I'm going to have my derivative, whatever it's going to look like, is going to pass through those 2 points. Up to this point, so up to this turning point, my slope is positive, which means my derivative is going to be positive as well. Then I take a look at what's happening on the other side of my turnaround point. So from here to here, my slope again is positive, so my derivative is going to be up in that direction. Now we need to figure out what's happening in the middle and where it's going to be turning around. Remember, this is where we talked about the fact that we need to find where the minimum instantaneous rate of change is. That's going to correspond to that point there. That means at that point, my graph is going to turn around. So it will look like that, which means that this one matches this one. Okay, last one. Same thing for these ones. So we want to take a look at where the slope of this is 0. So the slope is 0 at two places, which means that my derivative graph is going to pass through those 2 points, and I'm going to have a turnaround point that corresponds to where that center point, the inflection point, where it changes direction. And so I'm going to have this going like this. Now I need to know what the bottom parts of my graph are doing. So I'm going to look and I'm going to say, well, this to here on my original graph is a negative slope. So the graph of this will be down and negative. And on my original graph, this slope is also negative, which means that the remainder of that graph will go downward. By process of elimination, we have that graph. There are a few more examples for you to try on your handout. I will go ahead and I will post the answers to those to the VLE. And when you are done working through those examples, there's quite a few of them, just do them until you feel comfortable that you can draw the graph that corresponds to the function, the graph of the derivative that corresponds to the function. And go ahead and do the Desmos activity investigating graphs of derivatives. The link is posted to the VLE. That will give you a little bit more practice with this, and hopefully you will get some benefit out of that and have a little bit of an aha moment. There's no learning check-in for today's lesson or no exit ticket because I think the handouts are enough.